the Banach Steinhaus theorem. Let's change the pen, also called as the uniform boundedness theorem. The statement of that is that if you have what? So given the Banach space, n is given to be the non-linear space. Non-linear space. Suppose you have a family, so Ti of maps is a non-empty set of continuous linear operators of V into n. So you have a Banach space and you have what? N as a non-linear space. So T1, T2 and so on. Or rather it's just, if it is uncountable, then it is just denoted by Ti belonging to maybe say some indexing set lambda. So in this case it's a non-empty. Each of these maps, so maybe say T alpha is here. So T alpha is a map from B to N, which is linear as well as continuous. Okay. The further the property is that point-wise boundedness is given. So what do you mean by point-wise boundedness? Is that the set Ti of x is a bounded set for each x belonging to B. So this is point-wise bounded. Okay. So I belong to, if you want belong to lambda, as the case may be. Then the claim is that if this happens, then if you look at the operator Ti or the is bounded in the norm, then norm of Ti is a bounded set is bounded set of real numbers. That is, the set Ti is a bounded. So if we have norm Ti, so what we can say? So if you just allow me to write here, maybe what does that mean is that the set Ti, this would be as a subset of bounded linear maps from B to N. Right? That would be what? That would be a bounded set. So this condition over here is this condition. So what is the uniform boundedness principle? So you have a family of operators which are linear, that is linear and continuous map from a Banach space to a non-linear space. Okay, and the set Ti of x is what is bounded for each x belonging to V. Then what happens is that the norm Ti is in fact what kind of a set? Is a bounded set as a real number, or the set Ti's, the mappings from B to N in bounded linear maps from B to N. This thing, this is a bounded subset. Let's try to prove this thing. for each integer n, uh, look at the following set. What set? Fn. Collection of all those x uh, belonging to V, such that what happens? Norm of Ti of x, this is what? Less than equal to n for all n. Sorry, for all I. N is what? N is a fixed now here. So I is the option. So what is Fn? It's a collection of those points. So you have what? If you have maybe say, since it is what is given is that the set Ti of x is given to be what kind of a set? As the pointwise bounded. So if you take one particular x, so for example, maybe say if T1 of x, if suppose let's say n is maybe say 101. If n is just 101 in this case, then if suppose x belongs to f101, what does that mean? X belongs to f101 means what? So for the sake of brevity or simplicity, we'll consider, let's say this is a countable set. So what would I say? I1, 1, 2, 3. So T1 of x would be what? The norm of this thing is less than equal to 101. A norm of T2 of x, this is what? Less than equal to 101. Norm of T3 of x, this is what? Less than equal to 101, and continue so on. Okay, T3 of x, T4 of x, and so on. So the point is that if this happens for all x, suppose this family is just so this in Ti these are only T1, T2, and so on. If x is what satisfies this condition, then x belongs to what? X belongs to f101. Then such a x is in f101, as we have seen here. If the case is that what we could say is that if it is in 101, observe that f101 is there, then it is certainly contained in f102 and f103 and so on. Okay. Let's erase this part. So this is the definition of Fn. What we can observe here from here is that because these are the maps, so the B can be written as union of, so each of this Fn. So note first of all also that Fn is a subset of B. Okay, so you can have a side note over here. Let me write here. So Fn is subset of B for all n. Okay. So B is in fact, if I take n going from 1 to infinity, then Fn. So because why I can have this condition is that the set Ti of x is a bounded set, since the set pointwise boundedness is given. I belonging to lambda is bounded for each x. This is the case. So B is F1 union, F2 union, F3, and so on. So we can write that B is a union of this kind of thing. Note that Fn is what? Fn is a closed set. In B. Now B is the Banach space. So B is given to be what? B is a Banach space. B is a Banach space. So what can I say? Is that I have a complete metric space as a countable union of sets. Now the Bayes theorem, what would say about the Bayes theorem would say that a complete metric space is a category 2 space, so it cannot be written as countable union of nowhere dense sets. So one of the sets should be what? One of the sets should be having a non-empty interior. So in other words, what would happen is that so there exists a n naught belonging to sets of natural number such that Fn naught has non-empty interior. As non-empty interior. In other words, there exists an interior point, and interior point of what? Of Fn naught. Because this is a closed set, observe that Fn naught, because Fn, each of this Fn is a closed set, and this is the interior point in B, then what we can say is that there exists a closed ball centered around, so let's say the interior point, so there exists a closed ball centered at x naught. Okay, this is one, say, let's call this, say this is the point, so this is x naught, and with a radius, we say r naught, completely contained in Fn naught. Because this is an interior point. So let's say this is denoted by S naught. So S naught is a subset, is contained in Fn naught. This is a closed unit ball. S naught, the closed unit ball with radius r naught, centered at x naught, and x naught is the interior point of Fn naught. Okay. If you have S naught is contained in Fn naught, so what we can say is that if you take a point, so Fn naught is what? It's a collection of those x such that Ti of x. So here this is could be written as collection of all those x belonging to V such that Ti of x norm, this is less than equal to what? N naught for all x. So this is so x naught is a point here in S naught. So x naught satisfied. So note that Ti of x naught. So this is what just here it should be I for all I. Okay. Yeah. Now Ti of x naught would be what? N, simply N naught. So consider the point. So x naught is there. So you consider S naught minus x naught. So this is the what can be said about this thing is the closed ball of radius N naught, sorry, R naught of R naught, centered at 0. Okay. S naught minus x naught. So if you consider S naught minus x naught, this thing, and divided by R naught, then this is nothing but this is the closed unit ball centered at what? With radius. So this is unit. So this is a unit ball. So the radius is unit. Okay. Now what can we say about S naught minus x naught? So S naught minus x naught is is an object. So S0 is contained here. So norm of X0. So if you take any element in S0 also, so the same kind of object. Suppose U is there belonging to S0. T of U, norm of T of U if you take, that is also bounded by N0. So apply the triangle inequality. So if you take any element in T of S0 minus X0, then that would be strictly less than what? 2N0. So what we can conclude is that norm of the set T of S0 minus X0 is strictly less than 2N0. Okay, because S0 is a subset of Fn0 and so on. This is N0 and triangle inequality. Norm of T plus Tu plus Tv is less than equal to N0 plus N0, that is 2N0. So what would happen is that if you look at the unit ball, so let's call it by the name S, unit ball, closed ball in B, then this is S0 minus X0 upon 2 upon R0. So this is what would be the norm of Ti of S? The norm of Ti of S would be this divided by R0. So this divided by R0. So that would be less than equal to 2N0 divided by R0. Okay. So what we are saying is that this is true. Then this is true for all I. If this is true for all I, but this is nothing but, if you take in the definition of norm of Ti, so this clearly implies in the supremum norm of this thing, this is less than equal to 2N0 divided by R0. So this is this one, and hence what we have shown, that is, this is a fixed number, this is a fixed number. So uniform boundedness principle, we have proved that if this is a pointwise bounded, then it is what? In fact bounded in what? In the norm. That completes the proof maybe. Okay. Now let's take another theorem. It's a, suppose what do we have? X is a subset of non-linear space N. So X is there, it's a non-empty set. Okay, N is given to be non-linear space. This is here, non-linear space. X is a subset of N. Okay, X is bounded if and only if we have the following situation. The set f of capital X is bounded set of numbers for each f belonging to n star. So what we are saying is that if you have a non-empty set of n, if it is bounded, then the correspondingly what we have is that you take f of x is a bounded set of numbers. Okay. Bounded set of numbers for each f in n star. So if you take any map which is linear and continuous, so f is in n star means what? It's a linear map from n to the field. It's bounded, it's linear. If you take all this as a one particular f you take, and if you take elements in x, so so what does this mean? I'll just draw a line over here. What does that mean is that f of x, this set f capital X, f of x such that x belonging to capital X. So you take one particular f belonging to n star, you fix it. If you take one particular f and you fix it, then this set is what? F capital X is, in fact, the claim is that this is bound. If this is bounded, then X is a bounded set. If X is a bounded set, then this is happening for each f. So let's try to prove this thing. So we'll of course use the uniform boundedness theorem. So this way proof. So X is given to be a bounded set, and if you take f any belonging to n star, then if you take any x belonging to capital X, which is a subset of n, then norm of f of x is always less than equal to norm of f, the supremum norm, times norm x. Okay. Now this set, norm of f of x, is there. It is bounded by this and this. So this is a constant number over here. So what does that mean? Suppose if m is the bound for x, then if you look at norm of f of x, norm of f of x, the set such that x belonging to x, its bound is norm of f, the sup norm, times m. So this is a bounded set. This is the bound and so on. Now let's prove the converse. So conversely, this way. That is, given that f of x is bounded for each f belonging to where? N star. Then what we want to prove? That x is bounded as a subset of n. So what we do is that we look at the n and n star star, and in this case what do we have is that n, n star, n star star. Okay. So what do we have is that identification. So x, suppose x is in n, then it can be identified with x. So isometric isomorphism fx belonging to n star star, and norm of x is what? Is norm of f subscript x. Okay. So consider the following. F, this is given. So this is nothing but f of x such that x belongs to capital X. But this is again, by definition, it is nothing but f x of f, okay, such that x belonging to x. Now this becomes what? This becomes a bounded set. So if this is bounded, then what do we get? If this is bounded, fx of f here for each f, let's write for each f. So fx of f is pointwise bounded. If you look at this condition, if it is pointwise bounded, this is fx is a map in n star star. If it is pointwise bounded, then the claim is that this is a family of function arising from x belonging to n. So the set norm of fx such that x belonging to n, this is bounded by uniform boundedness principle. This is bounded, but what is norm of fx? Norm of f of x is what? Norm of x. So hence we have got that in the converse also. If f of x is bounded for each f for x non-empty set, then x is in fact bounded in n.